So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. There are still a few people coming, but let's continue. Yeah? This afternoon, we are very happy to introduce to you Chevarra Hansraj. She's a lecturer in the Applied Mathematics Department at Stellenbosch University. She did her PhD at UKZN in Durban not so long ago. Yeah. But she already been multiply awarded prestigious things like the Oppenheimer Memorial Trust Fellowship and the S2, A3 medal for her research in relativistic astrophysics, of which she will share something today. So Chevarra, thank you very much for being with us today, and we are looking very much forward to your talk. Thank you.
Thank you so much, and very good afternoon to everybody in person as well as online. It is a privilege to be presenting my research on the platform of NITheCS, my recent work in modified gravity. And as you can tell from the title of my talk, it is Beyond Einstein, Unravelling Cosmic Phenomena in Modified Gravity. So those are some really big words, I understand, but we're going to unpack the title bit by bit as we go forward. And just so that I can ease you into it, I've made us kind of a little roadmap to see what's going to happen or what's going to unfold in front of you. So the first place that I'm going to start is at Einstein's theory. So what do we know about it, and what are its advantages, its shortcomings, and then why modify gravity? Why do we need a modification if things are working so well? Then I will talk about the specific theory of gravity that I will be looking at, called the Einstein-Gauss-Bonnet gravity. And then I will discuss from my talk title, you would have noticed that I said cosmic phenomena. And I will be discussing two types. The first is curvature singularities, and then what's called the mass gap phenomenon. And then we will talk more about the cosmic behavior of the model, as well as the geometrical findings and extensions. So buckle up, it's going to be a ride. Okay, so let's start. Um, so we have to start with the main man, and that is, of course, Einstein. So Einstein's theory of general relativity is the most widely accepted theory of gravity. It's passed many big tests. For example, your solar system tests, like the perihelion precession of Mercury. You've got gravitational bending of light, as well as gravitational time dilation. And yeah, so it's passed many of these big tests, and essentially what it does is it describes how celestial bodies in the universe react, or yeah, their behavior, how they interact with each other. And these days, words like black holes and gravitational waves have kind of made its way more into popular phrases. I see a lot of people using it colloquially, some not even with a science background, which is really cool to see. But what is even more surprising is that Einstein's theory of general relativity preempted the existence of these constructs like black holes and gravitational waves. These things were said way back in the early 1915, around that time. And because of the really rapid advancement of technologies, now we can design large-scale experiments in order to confirm these observationally. And that's what I call the beautiful meeting point between theory and observation. And it's no wonder that the South African government has invested heavy capital in astronomy and aligned studies. And of course, Stellenbosch University is a big participant in that. So we have the theory of general relativity as our starting point. That's Einstein. And if you had to ask me in a nutshell of where I started out, essentially, I would say, if you ask me what I'm trying to do or what my research involves, I would say that I'm trying to find solutions to the Einstein field equations. We are interested in exact solutions. That's not to say that I want to slight my numerical friends. But the first prize is to, of course, find exact solutions to the Einstein field equations. And so essentially, in order to study the evolution of astrophysical objects like stars and galaxies, one needs to study the nature and behavior of their gravitational fields. And so naturally, we look to solving the field equations, which are embedded in the middle there. But they are a system of nonlinear partial differential equations, which my differential equations friends would be shaking their head and saying, that's the worst kind. So it's very difficult to get exact solutions to them. But a few well-known solutions do exist. And essentially what you're looking at right now is kind of a mind map, because these well-known solutions describe different scenarios, as in like different forms of stellar configurations. For example, the Schwarzschild describes a static black hole. Then if you add let's say if you add charge to the model, you'll get the Rice and Nordstrom charge solution, which is on the left in the bottom. And then if you add rotation to the model, you would get the Kerr rotating solution. And finally, if you have both charge as well as rotation, then you have what is called the Kerr-Newman approach. So these are the well-known solutions. Again, now we're interested in finding more solutions, so we need other techniques in which to solve them. Regular stuff is just not cutting it. You can ask my honor students, they will tell you the same thing. So one of the ways, or one of the other methods, ad hoc methods that you can use, is maybe coordinate methods, numerical methods. But my particular one that I'm partial to is the use of covariant methods, which leads to the topic of space-time decomposition. And that's a geometrical decomposition. And we use that in order to find more about the geometry of your gravitational systems. So to give you a brief motivation for why we need to use covariant formalisms, you don't have to take the words from me. We can actually have Einstein give us the motivation. So he said that the general laws of nature are to be expressed by equations which hold good for all systems of coordinates, that is, are covariant with respect to any substitutions whatsoever, or what is called generally covariant. So this statement is actually implied that the general laws of nature are purely geometrical. So that's why we want to study the geometry of space-time, or space-time geometry, through the lens of covariant methods. And that's what I'll be taking you through before we get to the fun modified gravity stuff. So if we had to start with space-time decomposition, giving you a brief motivation for it. So again, I have friends on both sides of the equator, in pure math as well as applied math. So you can look at the one that appeals the most to you. But essentially, in space-time decomposition, your space-time, which if you look at the diagram on the right, since I fall under the applied mathematics sector, if you look at the diagram on the right, it involves kind of taking a reference vector and writing quantities related to that vector that have physical meaning. So essentially, you have this hypersurface, and then you decompose the manifold. So you decompose the 4D space-time into space and time, where the time, that 4-velocity time-like vector, is orthogonal to the 3 space. And that's what we call the time-like congruence. And so we want to see how this congruence is expanding or contracting, shearing, rotating, accelerating. And that is essentially what space-time decomposition allows us to do. So we can explore these things, these astrophysical models, in a geometrical way. So we first start off with what is called the 1+3 decomposition. So the 1+3 comes from the fact that we are, covariantly factoring out time, and then you have a 3 space that's kind of left over. So you have your space-time decomposed like such, and then on the manifold you can define 2 important derivatives. One would be a time derivative, and another that's a projected covariant spatial derivative. Now, the main advantage of using this kind of formalism is that all the important information of the system is going to be captured in a set of well-defined geometric and thermodynamic variables, which are going to be written according to the time-like congruence. So to give you an idea of what this looks like, so this is a list of the different geometric and dynamic 1+3 variables, and it's a long list of stuff, but what you need to notice here is essentially that everything is written in terms of u. Okay, you can see u being heavily, mentioned in each of those equations, and this is because they're written according to this time-like congruence. And these, of course, are your usual suspects, so they have physical meanings behind them. So these are some of their names. So you've got expansion, acceleration, shear, vorticity down on the left there, electric vial and magnetic vial. The electric vial part is said to be responsible for tidal forces, and magnetic vial is said to be responsible for gravitational waves. And And so that's your kinematic quantities or geometric quantities. And on the right, you have your matter variables, which is, of course, your energy density, your pressure, your heat flux, and your stress. So another main highlight of this is that because these are all tensorial quantities, which I guess if you are a mathematical student, maybe that's not maybe something that you're so excited about. However, the main advantage of it is that when you use tenses, is that it remains valid in all coordinate systems, right? Because you can describe it in terms of tenses and its gauge invariant. So this is essentially the 1 plus 3 thing. And if you haven't heard of these concepts before, like volume expansion, shear, and vorticity, you can look at the schematic above. So volume expansion is essentially if you consider the fluid sphere, or you can be cool and consider the minion. If you consider the fluid sphere, the action of theta, which represents your volume expansion, will kind of lead to a different sphere of different volume, but kind of same orientation. And then you have shear, which is your distortion effects. Of course, shear can mean many things in different models, and it's not so different, I think, in gravitational models. So shear is your distortion of space-time, and so it's going to result in a distorted sphere that leaves the volume unchanged or constant, and the principal shear axis unchanged. And then vorticity is just another fancy name, I would say, for rigid rotation. So those are the various variables at play, and we are interested in how these things evolve and what we can say more about these variables. As you can tell, they have a physical meaning. So studying them, their interplay, finding relations between them is already physically significant in itself. So we're interested in seeing how they're related. Okay, so we talked about variables, and so obviously these variables have to be put together to mean something. So these are the variables that are really going to generate your field equations. And we know then that the arbitrary spacetime in this case, is completely characterized by the previous set of geometric and thermodynamic quantities. So when you provide an equation of state, then it becomes a closed, system. And then we can obtain the field equations, the Einstein field equations, in a different tensorial form than usual when we, look at the doubly contracted Bianchi and Ricci identity. So we don't use the direct Einstein field equations. We kind of look at it in a different setting. So this is pretty well studied in the literature. There's lots of stuff on 1 plus 3 decomposition. It might not be called that, but you will see that pretty much in quite a few gravity papers. But I want to talk more about a further decomposition and why this is needed. So you have here your manifold, again, your 1 plus 3 manifold, and you can decompose this thing even further. So you can decompose it according to another, what is called a space-like direction. And you can see there that that blue term, the 3 space, has been decomposed further. And so now all the geometrical quantities will be written according to both the time-like congruence and now a space-like congruence. And that is essentially what we do, so we can gain access to the scalars. And of course, this is optimized for spacetimes that have things like spherical symmetry. It's a very technical thing to say, but the main thing is you want to work with scalars and not tensors if you had to give you a choice. So this helps us do that and investigate spacetimes in that way. So again, the quantities on the left are the 1 plus 3 quantities, and you can see they've been decomposed further, written according to EA there. So that's what we have. All of them again have the pretty much the same meaning. It's just now you can see a more heavy presence of EA, essentially. And then we also have our thermodynamic variables. This is what our decomposed air total energy momentum tensor has. So this is on the right-hand side of the Einstein field equation. So this is what it looks like. And so we're interested in how we can use this framework to answer cosmological questions. That's the full set, as well as what the derivative means. There's 3 different kinds. You have a dot derivative, which is time-like along UA, a hat derivative, which is space-like along EA, and a delta derivative, which is onto what we call this 2-dimensional sheet. So this works in a 4D kind of environment. And then we can talk about the 1 plus 1 plus 2 equation. So what's different? So you can decompose the equations, just as is, or you can also use this covariance splitting. So you can use it with the Ricci identities where this RABCD is your Riemann curvature tensor. So this is responsible for the curvature. And you can project that RABC along your UA and EA and get evolution equations as well as propagation equations, as well as mixture equations and constraint equations. And that's going to lead to a list of like 33 equations. So, and here they are. No, just kidding, because I know, like probably the audience would have just like fled from here. So I just decided to put up an example of two of them. It went a bit easy on you guys. So this is an example of the equations at work. So this was a bigger project. This is what I investigated in my PhD thesis, which was the Kerr spacetime, and that I mentioned earlier was going to be the rotating black hole solution. And so we decomposed this system. So it took a lot to get to these equations. But again, just highlighting the advantage of using this formalism, you can simply look at the equation. Again, getting here is difficult, but once you do get here, you can simply look at the equation, and that can give you some physical insight. And how you see this is you look at that h variable there, which is the magnetic part of the Weyl tensor that's responsible for gravitational waves, which is on kind of one side. And if we take the other terms on the other side, you will see that in the Killing frame, which again, semantics, but in the Killing frame, the gravitational wave is a direct consequence of vorticity. And in the other frame, the gravitational wave is a direct consequence of the shear. So those are physical insights that you can deduce just by writing the equation in this tensorial form. So this is what we're interested in doing in various settings, this just being one of them, and one of them that's pretty cool. So when we get this list of equations, what do these equations actually tell us? Well, if we're still looking at the rotating black hole solution, essentially what it tells us is if you had to get into the spacecraft, and here's the interstellar reference that you were all waiting for, if you had to head straight to this rotating black hole, the equations will tell you how this spacecraft will stretch, twist, deform as we get closer to the rotating black hole. So that's what the equations will tell you. It's just essentially looking at the field equations in a different form, and investigating things geometrically. Okay, so I've applied this into many different backgrounds. So these are just a few of the stuff that I've worked on. So obviously the Kerr space-time stuff with conformal symmetries, radiating space-times, and so on and so forth. So I think one can say that it's been a pretty successful, voyage thus far. But obviously, you're looking to always one-up things, change the game, and so on and so forth. For example, the 1 + 1 + 2 formalism is optimized for spherically symmetric spacetime, but the Kerr spacetime doesn't have that. It doesn't have that simplification, but it was still able to give us new results. So we were thinking, what else can we do with this formalism to kind of, kick it up a notch? And essentially, we wanted to look at higher dimensions, which brings us to that question at the bottom there. If the theory of gravity and Einstein field equations is so successful, why do we need to modify it? Okay, so that's quite an interesting question. And the reason why, or one of the big reasons why, is that general relativity is a great theory. As we said, it's passed many tests. However, a critical shortcoming is its inability to account for the current expansion of the universe that has been confirmed from various observational, experimentation and instruments. So this is a critical shortcoming, of course, without referencing dark matter and the cosmological constant. So we're sitting with a bit of an issue here. We have a great theory, but it's not answering all the questions. So what do we do? Essentially, we're looking to extend it. We have a good source or good working point. So now we've got to build onto it to figure out the rest of how to explain the universe. And so that leads us to modified gravity theories, and there's a whole list of them. I mean, they just go on and on and on. So we're kind of working in that small area on the left hand side here. And of course, with these theories, they have advantages, they have drawbacks, they have trade-offs. So you've got to consider them pretty carefully. But the good thing is that we're working off of Einstein, and it's so well tested. So that's a very nice thing, because we can make that kind of our anchor and work back to a safe spot. So we're working in the area of higher dimensions, which you can see is on the left-hand side, kind kind of below there. And then you just go down and you just locate that little thing there which says Gauss, Bonnet, and Lovelock gravity. So we want to zoom into that because that is the theory that we want to look at. So why higher dimensional theories? I think it's not as in your face the whole higher dimensionality aspect of many applications of higher dimensions already. I mean, you have your Kaluza-Klein theory, you have string theory, brain world theory, where you have a 4D brain and a multidimensional bulk. Those all have higher dimensions kind of built into it. So they never kind of say, oh, it's higher dimensional string theory or brain theory. It's just string theory that involves higher dimensions. So under the bonnet, it's there. And yeah, I mean, the advantage of that, or the motivation behind that, is it can provide alternate explanations for dark matter or energy, as well as bypass singularities. It's also used in the quantum space. So it's something that is worth looking at, and we can have different types of gravity theories. You got higher derivative ones, higher order curvature ones, and that's the one that we want to focus on. So we're going to focus or zoom in on what's called Lovelock gravity, and this is our modified theory. So Lovelock, of course, is a second order, and it's named after the South African-born mathematician David Lovelock. And this in yellow there gives you what is called the action of this theory, and this is action of Lovelock or EGB gravity, which is Einstein, Gauss, Bonnet. I'm trying not to use too many acronyms, but we'll say GR is general relativity versus EGB, which is Einstein, Gauss, Bonnet. So those I'm going to try and just use those acronyms. Let's see how well I do. And so essentially, why we use this is because it's a generalization of GR to higher dimensions. So that just means that it's essentially Einstein gravity plus some higher order curvature terms. So when we switch those curvature terms off, we should get back to Einstein, our safe little pool that we're playing in. So if you look at the structure of the action there, that alpha term is what's called the Gauss-Bonnet parameter, and the blue term there, that L term, is your Lovelock term. And the good thing here is that it produces second order field equations, and they're written in a form like this. You can see things look slightly different from before. On your left, though, you have your Einstein tensor, so that's your curvature, and on the right-hand side, you have your energy momentum tensor, that's going to describe matter, and that comprises the matter-related part, so we're going to call that TABGR, and then the curvature-related part, which we're going to call TABGB. Okay, and that makes up the total effective energy momentum tensor. And that, of course, the curvature related one is written according to alpha, which is the Gauss-Bonnet parameter, as well as your HAB, which is the Langsos tensor. That's going to vanish when n is less than equal to 5. And of course, when we switch this alpha parameter off, which is how we get to the higher dimensions, we're going to get back or regain Einstein gravity. So this is essentially the theory of the gravity, that modified gravity, that we're going to consider today. And now getting more into what we are interested in looking at. So the cosmic phenomena that I mentioned in my title today is, of course, what I'm referring to is curvature singularities as well as the mass gap. So investigating these are quite crucial to our understanding of, I would say, the stability and structure of compact objects in higher dimensional theories, as well as for its comparisons to GR. So this further work is based on these two papers, and they have these specific buzzwords that you can look out for as we go forward. Promise it's not as scary, and I promise only to focus on the more intuitive equations. So let's see how I do. Okay, so curvature singularities. Let's take a quick pulse check with the audience. How many of you have heard of a curvature singularity before? Can we get some hands? I'm sorry, online audience, if you, I can't see you, but okay, cool. I got some people at the back. So essentially, there's this really good quote by J.A. Wheeler. It says, matter tells spacetime how to curve, and curvature tells matter how to move. So that is, in a sense, saying that general relativity is essentially geometry. Or you can say that gravity is essentially a manifestation of geometry. And so the curvature singularity is a place where the geometry breaks down completely. So that's there where the curvature of space-time becomes infinite. And you can observe this by measuring invariance that's built with the Riemann tensor that represents your curvature. And then this singularity will occur when the invariants blow up at some location in the space-time. And this is slightly an issue because Einstein's equations can't be continued past the singularity. We don't really know what happens beyond their account for it. So we need a bit of a modification to keep going. And then, of course, yeah, it's central to questions about black hole interiors, like, the information paradox. You lose information when you go into the black hole, and then, there's a problem there. So how do we deal with curvature singularities in modified gravity? And I think the significance of that, like we said, is curvature singularities will indicate a breakdown of the theory, right? Because geometry in essence stops. So in GR, essentially this means that the geodesics or rather space-time can't be extended. So space-time kind of ends there. So is it the same for modified gravity? Why do we even need to consider it? And then it could also point to quantum effects. Got many quantum people in the audience. And then we also can where it's necessary to modify classical theories. And another big advantage is, of course, the resolving or even the prevention or avoidance of singularities. How is this possible? So this will make up the rest of the talk. So we talked about curvature singularities, and now we'll come to the mass gap, which I'm sure it probably sounds really weird when you put those two words together. But essentially, what the mass gap is a minimum non-zero value of mass below which no static stable compact object like a star or a black hole can exist. So that is essentially saying that there's a limit or a certain bound, and beneath that, there's no horizon formation or no black hole formation. So we are interested in why this is happening, why there's this kind of delay. And this, of course, then could constrain the mass spectrums that will provide thresholds for observable data. But specifically, we are interested in what causes this mass gap to arise geometrically. And as you guessed, we'd probably employ space-time decomposition to help us, because when we consider higher dimensions, if you thought the field equations were difficult before, they're even more difficult now. So let's see what information we can glean from considering these specific phenomena. So firstly, we're going to consider what's called homogeneous and isotropic spacetime. So we're going to base our study in cosmology, and this is what the metric looks like. We have to look at the Freedom, Lemaitre, Robertson, Walker metric given there, and where that A represents the scale factor. And then you have, of course, the field equations that it will generate. So there's two of them over there, and as well as the conservation equation. And this is all in the presence of what is called a perfect fluid. If you haven't heard of a perfect fluid before, it's considered to be a good approximation to the universe because of it's smooth and there's no viscosity and stresses. So we like to use that model. It's also pretty simple to kind of consider. It's one of the first go-to models that you will probably look at when you're considering specific theories. So we've got that. And now I hope to you kind of draw your attention specifically to the equations. And you can consider them for now as differential equations, and I'll help you unpack the physics behind them. So if you take equation 1 and 2 as a combination of them, linear combination of them, we can obtain a double dot. So a double dot, I think, is located somewhere on the second equation, somewhere in the middle. And then we can back substitute, almost like get rid of the a double dot to find, then we solve for a dot squared. Okay, so when we do that, we get an expression for a dot squared, which we can then kind of break down step by step and then write this t integral formula here. So a dot squared is dA over dt, and then we solve, essentially we integrate and get this t equation. So what we find is essentially implicit solutions for cosmic time. So we create, or yeah, we sort of develop or create a framework to relate your thermodynamic properties, like your energy density as well as your pressure, to the temporal evolution of the model. So we get these implicit solutions, and then what we do is we use the enthalpy function that's defined according to this very famous textbook, Relativistic Cosmology, that's authored by Ellis, Martins, and McCallum. And we take this m function, we write it as such, the integral exponent integral d mu over mu plus p of mu. mu being the energy density, P being the pressure, and then we use that to transform these field equations to help us find solutions. So if we take the derivative, like so in green, then we can write kind of the orange, and then what we can do is we can write the energy density in terms of this m function as an m inverse via the inverse function theorem. So inverse function theorem, hope you remember your calculus. No. So we can then plug that mu of t back into our top equation there. So there's mu under the square root sign at the top there. So that's what we're interested in doing. And when we do that, we get an integral that looks something like this. So essentially, we've just replaced the mu with the term that with that red term that we found. And yeah, we can see that on the right-hand side, it's a factor of this of the scale factor a. And now, essentially, what we do is we just conduct our analysis on this integral, and we do it in a very intuitive way. So if you notice there, as a of t is monotonically decreasing, either in the future or the past, you have mu being monotonically increasing. So there should be an epoch, which is certain like time period where the negative term. So if you can see under the square root, it's like -8 alpha, so on and so forth, right? So that's the negative term, and then you've got a positive term coming after that, after the plus sign, right? So that's when I mean negative term, positive term. So there must be an epoch when the negative term under the square root is going to cross the positive term, and that then is going to lead to a complex integrand, right? So it's going to cross each other, lead to a complex integrand. And that's bad because evolution of the model cannot continue beyond this epoch, where the scale factor a of t is going to attain what is called the minimum positive value a min. All right, and then this cannot become any smaller, and it's going to be true for any equation of state that's written in the form p is a function of mu. So this, we can call bound or limit, kind of eliminates any curvature singularities in the future or past, where, as we require for singularity theorems, where the a of t must tend to 0. So it doesn't have to be so in these cases. And then these models wouldn't include things like your Big Bang, big crunch models, as well as any homogeneous type of collapse, like the Oppenheimer-Schneider. It does not terminate at the singularity. So this is quite distinctly different from your general relativistic case where you have m-1 going unbounded. We always kind of want to check in, remember, on what the differences are, because why modify it if there's no advantage to it? So we always just check in and make comparisons. But we can summarize all of these findings into a neat theorem that states an n-dimensional homogeneous and isotropic perfect fluid spacetime in Einstein Gauss Bonnet gravity contains no curvature singularities either in the future or in the past, meaning if you evolve forward or you evolve backwards, without violating any energy conditions. So that's quite interesting, and you can also kind of see it intuitively if we consider the schematic. So your a double dot represents your cosmic acceleration, and you can write that in terms of effective quantities of your energy density as well as your pressure. So if we work out what a dot is from before, we can find the derivative, and you can see it's written in terms of that s function there. So if you look at that double derivative, what you'll notice is s being in the denominator there. So that should be pinging you already, like, that's going to be undefined. So yes, so what we notice is as s goes to infinity, your a double dot equation is going to go to, I mean, as s goes to 0, your a double dot equation is going to go to negative infinity. And that essentially indicates that there's a freezing in the collapse process. So to tell you more about collapse, maybe like, what is it? Black hole collapsing, what's happening. So essentially what happens when a star reaches the end of its life and it's about to become a black hole, there's a thing called gravitational collapse, where the star collapses into itself. So that would be a makeshift definition of black holes. And so, yes, you would get a freezing of the collapse process in the future or in the past. And this also tells us that our configuration is tending to aim in for an infinite t asymptotically. So it's asymptotically approaching this amen. Now, again, okay, maybe those are just two big words, but if we look at the pink block there, you've got the double derivative there. So your cosmic acceleration will start off to be positive, and when it's going to 0, that second term is kind of going to dominate and head towards a negative infinity. So that's quite novel in this kind of study. So if we see the application of something like that, so now we're specifying an equation of state. So we just take a linear equation of state like the green one there. So P is equal to CS squared mu. Then we get something of that form of the integral, and then you can kind of plot that using some parameters. So what we can see immediately, the Amin is going to depend at the bottom there. You can calculate your Amin specifically now that you've specified your type of equation of state. You can see that it depends on both n as well as alpha. And something else that we notice is there's a peak, and that happens at dimension 9. So that indicates that this is a topologically significant dimension where the Gauss-Bonnet contributions kind of peak. And or you could maybe phrase it in a more, physical way, where you can say it's the optimal dimension where the repulsive effects of the higher order curvature terms are maximized, and so that prevents the formation of singularities most effectively. And it's nice to have this correlation because there was a study done by, I think it was BC Paul, where after the critical dimension 9, the volume starts decreasing. So it's nice to have that correlation between the two studies, which is quite interesting. Now, in my remaining minutes of the talk, I will develop the concept of the mass gap. So a different type of, like I said, when you consider different metrics, you will then consider different types of stars. So if we consider something like a radiating star, this is a solution to the EGB field equation. It's called the Bulwer-Diesel, radiating Bulwer-Diesel metric. And this is said to be a generalization of the Schwarzschild solution. So it looks something like that in pink. And you can get the GR limit by taking alpha to 0 of f, which we use the positive branch to avoid any, the negative branch rather, to avoid any Gauss or anything, which reduces then your Bulwer-Diesel metric to a 5D collapsing pure Vedia spacetime. Again, very technical words, but essentially it reduces to this radiating solution because of the presence of a specific type of matter, which is called type 2 matter, in the presence of a null string fluid. So this is just a new context, rather. We have a radiating thing, and we're also working in a specific dimension. So we're working in 5 dimensions. So we want to see what the effects of this will cause if we do a decomposition on this. So uh, talking about gravitational collapse and the mass gap, what do we know about the singularity? Well, it has been quite well studied. Meda said that in 5D Einstein Gauss-Bonnet gravity, there's a massive time-like naked singularity, formed not which is obviously not present in general relativity. And then further studies kind of tell us that the collapse is going to terminate with what is called an extended, weak, and conical central singularity, according to this Hawking-Ellis classification. Big book that is initially naked but subsequently leads to a trapping horizon. So this mass gap, just to remind you, of course, is that delay in horizon formation, where the central mass is below a threshold value. So we want to know how this arises geometrically for a general mass function, and then provide more insight as to what happens near the central singularity. So the way that we do that now is, because we want to investigate things geometrically, we have to use space-time decomposition. But we've discussed space-time decomposition in 4D only, like we were working in general relativity. So how do we extend this to 5D? We actually don't have to do all that much. It's pretty much a similar thing, except that everything just changes dimension. So now you'll have a 4 space instead of a 3 space, but it's the same kind of concept and literally the same definition. The great thing here is that I mentioned that it reduces to the Vedia metric, and the good thing is that we are in spherically symmetric territory, so we get to work with scalars. We can say goodbye to tensors, and we can make some deductions based on your scalars. So looking at gravitational collapse, if you kind of analyze that green equation there, you can match your space-time at m naught, the shell interior, to Minkowski space-time, the exterior to, as we considered, the Bulwer-Diesel space-time, and then you can pinpoint your singularity. Now, something very interesting happens there is that there at the where the singularity is pinpointed, all the metric functions are going to be well defined and regular, provided that m naught is finite and it's greater than or equal to 0. So that's quite interesting because that doesn't happen in GR. And if we had to calculate this invariant that's related, the Kretschmann invariant, there would be a much slower divergence that's noticed. So that's weird, weird behavior. But the apparent horizon of the black hole is going to form if you take that F from the metric and you equate it to 0, and then you solve to find the RH being the horizon. So if we just look at that red and yellow equation, again, we can do things very intuitively. You can see that if you take m naught, m naught being 0, RH is not going to be 0, right? It's going to be 2 alpha. But this is the case in the modified theory. In Einstein's GR, it does give 0, which means the central singularity formed from the horizon is formed from the central singularity. Here, it's not forming from the central singularity. It's only forming much later. So there's a delay. You can see there would be a delay in this case. If you switch the alpha term off, that's going to give you Einstein gravity. Then you'll get m naught is equal to naught, right? That's then you say the horizon forms from the central singularity. But in the modified theory where alpha is very much switched on, you're not going to have that equaling to 0. So we that prompts a further investigation. And then this is just a diagram to show what I said before of the shell interior, exterior, and then the mass gap kind of located in that region. So the region of delay, that's 0 less than m of v less than 2 alpha, is where there's no black hole formation because they have not attained a threshold mass value that's governed by this parameter. So uh, the idea then is, so we've considered a general mass function, everything is written for that. So we want to know what are the contributing factors to this mass gap during which there's no black hole solution. Why is it not possible? And if we look at that, then we'll do some limit analysis. So let's go back to first year. Again, it does take a bit of time to get to these results, but I'm sticking to the intuitive stuff. So let's look at these limit analysis. So if we consider the limit r to 0 for these general effective geometrical quantities, then we will see that that's how we determine the behavior near the central singularity. So if we want to look at the behavior, we've got to take r goes to 0. That's where your singularity is. Okay, so if we do that, we find that some quantities blow up, but the quantities over there in blue, yellow, and green remain well defined. So that's quite interesting because in GR they blow up for all of them, where M naught is well defined. So that leads us to the research question. Then when we see that, we think to ourselves, okay, so what are the functions, the mass functions, M of V, for which at the central singularity the quantities theta, a for acceleration, and sigma, which is your shear, are finite. So we want to know what are these. If you look at them, they kind of have a similar construct. If you look at the top, you have m comma v there, so you've got some derivative of m at the top there, and at the bottom you have the mass function m of v. So you can kind of make a general statement there, or like a proposition, that for all mass functions mv with m greater than naught, m naught at naught is well defined. If the condition m is less than 2 alpha, where there's is satisfied, where there's no horizon formation, and this limit, again, see we took like a general form of it, is well defined, then the geometric quantities relating to expansion, acceleration, and shear are well defined at the central singularity. So this again is quite interesting because theta, which is our expansion variable, is remains finite. So that shows that the central singularity is not a sink for time like geodesics. Remember how I was talking about space-time's stop at curvature singularities, but here we see that the space-time is extendable, and it will result in black hole formation that does not violate the energy conditions. So big advantage of modified gravity shining through there. And then since your space-time is extendable, the singularity, according to classifications, must be weak in nature, therefore is conical, and that's kind of further emphasized by the horizon forming much later. It doesn't form during the mass gap, and we can look at this also kind of, again, just with analysis. If you consider a self-similar model, so when you take the mass in the function that's green there, that's your horizon function, then in the middle, and then the mass gap between that category, you can kind of make a comparison between the two. So if you look onto the left, these quantities remain well defined. And if you look on the right, if you take r goes to 0 there, you can see the heavy presence of r in the denominator there. So this is going to blow up like, so um, So yeah, so that then points to the fact that in GR you obviously have strong coverage singularity, and in 5D EGB you have a weak singularity at in the center. So yes, that's to say, to draw these two studies together. We did them both in this modified field of gravity, and essentially these extra curvature terms can be considered to kind of induce an energy momentum tensor that has negative pressure, which either weakens the singularity, as we saw now, or it avoids it completely, as we saw before. So from before, we had that A dot dot equation, which was written in terms of mu, energy density total, and pressure, the total pressure. So there will be a point where the pressure is negative, or it crosses the, the mu term. And yeah, that's, so this is the explanation for that. And these studies kind of highlight how this Gauss-Bonnet invariant alpha affects the evolution of the model, as well as the nature of the final state of a continual collapse. Again, we're interested in terms in things like gravitational collapse because of the implications of that, like black holes and so on and so forth. So this was just essentially a long geometrical kind of kind of exploration of of what of these critical features like curvature singularities, as well as the mass gap. So it's a geometrical look at, or under the bonnet, or bonnet, look at these models. And despite, the current limitations, or you can say maybe the nascent stage of experimental detections, I think, it's important to investigate these theories, to have like a positive foot forward, to get steps closer to having a more complete theory, although, jury's still out on that one. And of course, there's a variety of ways. You saw that schematic, a variety of ways to approach it. So you have to really carefully consider also the trade-offs when you pick a modified gravity theory. And the reason why we study, concepts like black holes and gravitational waves is because Einstein's original theory preempted this. It's there. There's implications of it, and so we want to probe these things in higher dimensions. I think to end up in a more personal, I think it's always kind of fascinated me how gravity is, as I said, essentially a manifestation of geometry. I will also admit to not liking geometry as in school, but the irony of life. But it allows you, I think, using tools like space-time decomposition kind of allows you to unpack the geometrical features of these very complicated astrophysics and cosmological models. It fascinates me that we can just take things, and explore them on paper via mathematics. So that's our cosmic journey for today, and it's time to get off the ride. But I hope that you've learned something new, or you've learned something, a new concept, or maybe you're just going to be that friend now in your friend group, and you're watching like Interstellar or Gravity or Oppenheimer, and then you're going to be, well, I know a few things about this, and then you share your knowledge with them. But for the future, I hope to kind of investigate more gravity theories in this way, although that's kind of complicated, and we can chat about that. But yes, thank you very much for attending the colloquium, both to the in-person audience. Very nice for all of you to come up and support, as well as to the online audience. And I always love to kind of present my work, so I would also like to thank NITheCS for giving me this platform to do so. Thank you very much.
Yeah, thank you very much, Chevarra, for the very nice talk. And you mentioned the online audience, and I think I'm very pleased that I think all NITheCS nodes were present today. So welcome to all the NITheCS nodes that logged in
Okay.
the Zoom webinar. Are
Thank
there any
you.
questions for Chevarra? Okay.
Thanks for your interesting talk. I had a question.
Yes.
What would be the fate of principle of equivalence for this Einstein-Gauss-Bonnet theory?
Yes. So I think in that, wait, let's see if I can, did I mention that one? I was just saying that the essentially what is good about the Einstein theory is that you have, of course, your diffeomorphism invariance, right? You have also your Lorentzian, the boost, and so on and so forth. So all of those things are kind of covered. So yeah, I mean, I think it's pretty stable in that regard. I think though in a lot of cases, some theories might not be stable in that way, but the general covariance is preserved, I would say. Yeah.
But
So.
but but in this Einstein Gauss-Bonnet theory, you added the higher order curvature term.
Mhm.
So how one can believe that the geodesic deviation equation will be still of the order of curvature, and whether it can show some mild violation because the Einstein-Hilbert action carries some higher order corrections.
Yes, but it extends the theory, right? So it's the basic theory as well as the higher order curvature term. So it doesn't really matter because the deviation then isn't like modified, you know. So I would say it in that way.
Okay, and another question is that what whether the black hole solution for this modified Einstein theory or Gauss-Bonnet theory will have the thermodynamic interpretation?
Um, yes, I mean, yeah, I think, I mean, you mean in probing those, the thermodynamic variables as well. We've done that in our study. We've probed the thermodynamic variables, but I didn't get into that too much because it got, it got a bit too technical. But yes, you can probe those things. In fact, in the paper, what we did was we took the various variables in the decomposition method and we separated it into the matter part, which is the Einstein part, and to the Gauss-Bonnet contribution. So, Gauss-Bonnet, and so you can separate those things. So yeah, if you choose your matter fields appropriately, we used perfect fluid. So yeah.
Okay, and my last question is in Einstein theory or in the general theory of relativity, we always discuss the geometry of space-time. But do you think that why we are not considering about the geometry of momentum space? And what would be the fate of momentum geometry? And where you are always discussing the geometry of space-time?
Me particularly. No, I'm just kidding. I think. Well, I mean, I you mean like momentum in the sense like so not like energy momentum tensor. You mean like uh, in what way is what I mean.
Because when we measure any event, we always provide the in terms of the energy and momentum.
Mhm.
So how you define the space time without energy and momentum? So why we're not? I understand that in general relativity, in the momentum space play the passive role, space time behave act as a active role. But whether any possibility that the geometry of momentum space also play the fine role in considering the modified theory of gravity?
I mean, I don't know if I've really looked at that. I mean, I wouldn't say so. I mean, I feel like in that case, it would be like probably like Hamiltonians, like formulation or So yeah, I'll have to look at that, but I'm not particularly
Okay,
sure about that. But cool,
okay,
that'd be something to
okay.
check
Thank
out.
you.
Cool.
I think there is another question here, Surab. Yeah, maybe less technical. Thank you very much for your very nice talk. What is the possible physical, if there is
Mm.
one, physical interpretation of these higher dimensions that are now included in the model?
Yes, the physical interpretation. So obviously we're working at like a very high curvature regime. I don't know if you meant experimentally or like observationally or like what does it tell us?
So the standard one with 3+1, the three dimensions is the three
Three
dimension
space.
of our
Yep,
intuitive space, and the fourth one is time dimension.
that's right.
Now, in these higher dimensional models,
What does it
what
look
are
like?
the other dimensions?
Yes, so it would essentially be again time, and then it would be a four space where you choose a preferred spatial direction. In most cases, we choose like a radial direction as such, and yeah, and then it would be essential. Now we don't have that two space. If you're looking at the further, 1+1+2, we have a three-dimensional hypersurface on which those quantities are there. So yeah. That would be an idea. But if you maybe were talking about, so that would be like a topological, I guess, consequence. Yeah, is how I would say. So it's like it's one direction, and then a 3D hypersurface that's there.
So maybe I misunderstood the dimensionality. So,
Hmm.
there are three spatial dimensions.
Yeah,
In
in four. Oh, okay. If we work in 4D, yes. Mine was in higher dimension. So essentially, it's one time and four spatial. One and four, yeah, and then one and one and three. That's how we decompose it, as opposed to
but you
the.
do consider the case when it's more than four. don't
Yes,
you?
yes, yes. We could
That's where the
yes.
theoretical simplifications occur.
Exactly. Yes, yes,
But
yes, yes, yes.
do these higher dimensions, additional dimensions, do they also have a physical way of viewing what that means? Or
Oh, a physical way of, yeah, I suppose you can't really draw a diagram, which is why I did it. I kind of cheated a bit and I did it in the 4D space and then try to cleverly just be like, well, it's the same thing in 5D. So it's conceptually difficult to, observe these things. And I guess that is maybe an ask for experimental, detections as well as to how we're going to detect high dimension theories. I think it's, like I said, it's still in its nascent stages. Right now, they're trying to detect it indirectly. So from what I understand from experiments like the Large Hadron Collider, they're looking at determining whether, they said when there's like high energy proton collisions, there's like these things called gravitons, and they're trying to detect that when it like, that's kind of like a consequence of a higher dimension or like very small black holes. So they're trying to detect things indirectly. But amazingly, even though I think they had mentioned like 3 different things they were trying to test, and although they couldn't, come up with anything significant, they said that the results were inconclusive about higher dimensions, whether they exist or not. The results are inconclusive because they may be testing at too large a scale. So yeah, I think So we have to still check that out.
one of our online participants is very keen to ask a question. Can we please allow Professor Dutoit Strauss to ask the question in person?
Hello, can you hear me?
Yes, we can hear you, Dutoit. Please go
Yeah,
ahead.
this is Amara speaking from NWU.
Hi, Prof.
You're using
Hi,
another
Chevarra. Thanks for the
universal
excellent
Zoom
talk.
license.
Can you take us to the slide where you started with the homogeneous and isotropic n-dimensional space-time?
Yes, hold on. I am getting there. It's just taking a bit. Almost there. Almost. There.
Well, yeah, this one.
Okay.
So here you assumed a positive pressure.
Yeah.
With that kind of scenario, we know that at least in the standard GR, you'll not get an accelerated expansion.
Yeah.
So have you considered that some limitation of this theoretical framework? Or have you tried if in this specific model you can actually get a positive pressure?
So a positive pressure. So when we look at the enthalpy function, right, which is what we kind of replace our thermodynamical variables with, you've got your mu and your p of mu there. So that keeps it positive. So we're only interested in kind of when the integrand is positive and definite. So maybe that would be a flaw, but I don't think so. I don't know if I'm answering the question correctly, but yes.
And in fact, this is my second question. How did you manage to get that kind of energy density without assuming a pressure that is zero? It looks
Without
like from the form of this solution, it looks
Yes.
like you've assumed pressure to be zero already in this.
No,
In this
you see, because we've solved equation. Wait, let me go back. Yeah, there we go. Because we solved equation 1 and 2, like we've taken a linear combination of that, pressure kind of got eliminated. So to work it back into the equation, because we took a combination, to work it back into the equation, we use the enthalpy function, which is written in terms of the energy density and the pressure, so that we can still comment on the model.
Okay, then if, in the next slide, if you look at the energy density solution that you gave, and reducing that to GR, for example, the standard GR with n equals 4, you get that solution only if you have a zero pressure. So that's kind of problematic.
Okay. Yeah. Okay. I will look at that. I perhaps maybe it's not coming to me intuitively right now, but I will look at that. It seemed to be okay though, because I know that a similar thing was looked at in the GR case, and we were essentially extending this to higher dimensions. So yeah, I know it does. It implies pressure is positive. So yeah.
Yeah. Thanks.
Thank you.
Okay.
Thank you for joining.
Thank you for the question. Are there more questions? Here we go. Please.
Sorry, Doc. Thank you for the talk. What you said something about how high dimensions relate to gravitons. I didn't hear you quite.
Yeah, I mean, I don't know too much about the experimental part of it, which which comes about with the gravitons and so on and so forth. However, I was just mentioning that in the sense that in order to detect higher dimensions, the Large Hadron Collider tried to detect it indirectly because we don't know how to probe higher dimensions at the current stage that we're at. And so what they looked for was when there's high energy collisions of protons, it has, gives off these gravitons, and they want to see whether they can observe this. It kind of leaks into the extra dimensions. I read up on that one a little bit. That's how I know. So that's where that comes from. So if they detected that, then they would say, oh yeah, higher dimensions kind of exist. But I know that like in like quantum theory, I think it's kind of believed that gravity would propagate as a massless particle called a graviton. So yeah, but I'll leave that to the experts.
100%. I think also it will help everyone to know that last week there was a colloquium from Prof. Igor. He was focusing on gravitons, the possibility of
That's right.
of
Gravitons.
being able to measure them.
Yes.
Yeah,
Yeah, exactly. So yeah, so maybe that will happen, but again, I think because it was inconclusive, maybe it's at too large a scale. Perhaps, yeah. So again, inconclusive for now, but yeah, we'll see.
Yeah, and if everyone is interested on that one, I think it's also on the NITheCS YouTube.
Cool.
Yeah.
Thank you for that word. Any more questions? Here we go. Sorry, just a second, please.
Right. Now, can you explain to me that last scene in Interstellar where this guy is looking through the books? I don't know what is going on. It's a cool movie. Don't know how it ended.
I love that. Yes. So essentially, I mean, there's many different. I guess it's like a kind of an open ending, but yeah, I think I actually don't remember it too well at this current time, but we can have a further discussion on that after. Yes. So I think that's the great point to be like, time for snacks.
Thank you. But I think Donovan has some
Oh, sure.
questions from the online audience, from the chat.
Just one question. How does EGB avoid invoking dark energy to explain the acceleration of the universe?
Yes, so it is like an alternate kind of explanation for that because we don't have the mechanism of dark energy built into it as yet. However, if you kind of wanted to probe dark energy or that type of thing, then you would have to choose a different equation of state. So the one that I used in this talk was a linear equation of state, but there's a nonlinear equation of state called the Chaplygin gas, which is said to kind of mimic dark energy or something. So you could kind of probe that inside the model as well. And we did do that in the paper, but again, not for the audience today. But yeah, and to say on Interstellar, Kip Thorne, who won the Nobel Prize, was a consultant on that. So it's done pretty accurately, and I think the picture was actually quite similar to what was kind of found. So I think it's a really big hallmark in in gravity. So yeah, in EGP gravity though is essentially introducing extra curvature in a way that can explain the expansion of the universe. So I believe that that's where the modified gravity, what it's explaining, the accelerated expansion of the universe. Yeah.
Okay, I think all good things come to an end. So Chevarra, thank you very much again. And this time I won't forget to give you as a little reward
Thank
the
you.
Visitku magazine.
Thank
so
you.
thank you very much. And I think yeah, and thank you to the online participants
you.
and to the physical participants. There should be some snacks and drinks outside waiting for us according to plan. But you never